So, let's come to one of the most complicated properties we need for fluid dynamics. And that's maybe one of the last fluid properties I have to teach you about. And this fluid property is called the viscosity. Viscosity, yeah, I think you all know density, you know pressure, you know temperature, you know speed of sound, but viscosity is something you do not really know so often. But viscosity is also a quantity you really need to make your fluid dynamic calculations. And we want to speak about viscosity for Newton fluids. I introduced you what Newton fluids are a bit before. And here's a short movie. You maybe also know it from the Moodle module, and it shows you a bit what this viscosity is, more or less. Yeah, viscosity, you can also call it how liquid a liquid is. Maybe that's a bit of explanation. Here on this side, yeah, you see the blue liquid. It's like an alcohol or water, and it has a really low viscosity. Yeah, so it can flow really fast. And on the other side, here on the right side, you see a liquid that is like honey. Yeah, it has a high viscosity, like a really high viscosity oil, or fat or mustard, and it flows a bit slower. So this maybe explains you a bit what the viscosity is. But here we have, in this lecture, we have to go more into detail, because the difference between different viscosities has a high influence of the design of power plant, of plants or so. Yeah? And let's go to the definition of viscosity. Yeah? For example, imagine you have a pot of water or a river or something, and there is water inside. Then you have a movement of air on the top, and it pushes the water to one, and you get a velocity in the water. But of course, I already taught you, at the bottom of the river, really at the ground, you will have no velocity. Velocity will be zero. So you have a gradient. You have here a low velocity. Velocity will be higher, higher, higher to the top velocity at the upper boundary. So, and how this gradient behaves, depends on the viscosity. So we can introduce the so-called dynamic viscosity. Okay, maybe that's something I have to introduce also. We have two different viscosity values. We have a so-called dynamic viscosity, and we have also other viscosity values. So, and first I want to tell you something about the dynamic viscosity. The dynamic viscosity, we use the symbol eta. It's a Greek symbol, it looks a bit like an N, and it gives you the relationship between the gradient and the shear stresses inside the fluid. So if we have special gradient for high velocity, low velocity, and we multiply it with a dynamic viscosity, and we have a high viscosity, we get much more shear stresses inside the fluid. And if we have a really low velocity like water or alcohol, we get low shear stresses inside the fluid. Okay, how can we measure this shear stresses? We can measure it if we take a ground plane and another flat plane, we push it onto this plane, we put an oil or a liquid between these two plates, and then we shift the plates around, and then we get a gradient inside the fluid, and we can measure the force, and we can measure the shear inside the fluid. That's how we measure it. And if you can imagine you have two, for example, two blades of glass you put honey inside and you push the blade, you do more force if you have honey than if you have water between the blades. Okay, what are shear stresses? What are shear stresses inside a fluid? Shear stresses give you, if you shear it, if you have a force on you can also have shear stresses in a solid or in a fluid. You do this experiment, you put the two glass plates on each other, you shear it, and if you have more force, if you put more force with your hand on it, you get higher shear forces. If you put less force on it, you get lower shear forces. Okay, here's also an experiment I want to show you, because if we deal with oil, if you look at oil, motor oil for example, or oil for other machines, it is really important to have the right viscosity. So if you have a car, you want to buy motor oil, you always have to look carefully which viscosity my oil should have. And here's an experiment. You can look at the slides, there's also a YouTube video online for this experiment. I took it from the YouTube video, and it's a video about two vessels, two pipes, glass pipes, and you have one pipe with a high viscosity, one with a low viscosity, and you put a small metal ball inside these tubes, and when you have high velocity, the ball will flow slower. When you have a low velocity, the ball will be faster. Maybe take a look at the slides, go to the link, and then you can have a look. And with this experiment, you can also calculate your dynamic viscosity. And I told you we have two different viscosities. We know the dynamic viscosity, it's to calculate the shear forces. We use a simple eta for kinematic viscosity, but we also have the so-called dynamic viscosity. Okay, here's the definition of the so-called kinematic viscosity. The kinematic viscosity is a dynamic viscosity divided by the density of the fluid. So if you know the density, if you know the kinematic viscosity, you can calculate the dynamic viscosity. You convert it into each other. Okay, but I have to mention, this is a fluid property. The viscosities have to be measured, and then they make a big table, as you write down the viscosities, and you have to look up the table, and also the viscosities will change with temperature and with pressure. Now, change with pressure is not so much, but the change with temperature can be a lot. If you have a motor oil and the motor block is cold, then the viscosity is higher, and if it gets hot, the viscosity gets a bit lower. Okay, here is a conclusion, and now it really gets tough. Now it gets really complicated. The conclusion is just for Newtonian fluids now. If we have a Newtonian fluid, we have the behavior, here's the gradient, times the viscosity is the shear stress. The shear stress is inside the fluid. So the shear stress depends in a linear behavior to the gradient. And this is described by only one value. Then, if this is fulfilled, we have a Newtonian fluid. But I will show you soon, we also can have non-Newtonian fluids. And this makes it more complicated. If we have non-Newtonian fluids, this dependency will not be linear. It will be, or can have an additional factor. Or show you some examples. Okay, but first we are in the field of Newtonian fluid. Everything has a linear behavior, and you have to know Yeah, it makes it again more complicated. Viscosity behaves different if we have a gas or if we have a liquid. Yeah, if we, for example, have a gas and we go up with the temperature, we have higher viscosity. Yeah? If we have a liquid, we get lower viscosity. Now that's a bit complicated. And here also some viscosities. You can see viscosity of water is much higher than the viscosity of air, and that's something you know. Air is much more liquid than if you compare it to water. Okay, that's again a sketch, a graph, where you see the behavior or the influence of temperature. If we have temperature and a liquid, we get higher temperature, the viscosity gets lower. Please imagine, for example, motor oil. If we have a motor clock, we make the fluid hotter, we make the oil hotter, then we get lower viscosities of the liquid. Totally different is the behavior with gas and steam. If we have gas and we make the temperature higher, the viscosity rises. Yeah? This is a strange behavior, and maybe you do not really know this behavior from your daily life, but I can give you an example. If you make a fire, the viscosity of the air inside the fire rises. So sometimes if the firemen have to go into a house and it's hot and you have hot air, it's more difficult to walk there for the firemen than if you compare it with colder air. Yeah? But that's something you probably do not really know it from any experiments. Okay, but keep it in mind. Okay, here again is an explanation. If you have a liquid and you rise the temperature, the molecules get faster and faster, and this means they have more space in between, and the viscosity goes down. If we have a gas, and normally if we have a gas, the distance between the molecules is not so really big, yeah. But if we make the temperature higher, the molecules move very fast and they hit each other, and then we get a higher viscosity. Okay, that's a bit tough, I know, but you will have to know this circumstances. You get some tables and you have to look it up. Okay, here again, explanation. And here is an example for a table, fluid properties of water. And that's something we will work a lot with when we make the exercises. How do you have to read the table? You have here temperatures from 0 to 300 degrees. And you can look at the density. Yeah? Density gets lower. You can look at the dynamic viscosity. Here is the saturation pressure. We don't need it yet, but you can have a look at the dynamic viscosity. Gets lower, and the kinetic viscosity also. And now if you have to solve an exercise, you have to look up into the table, take the temperature you need, and look at the dynamic viscosity. So here is also again a table we use for the exercises, for example for different fluids, and you can have a look. There are a lot of different fluids. For example, there are quicksilver, natrium, methane, benzol, also a hydrocarbon, air, steam, and they all have, depending on the temperature, different densities and different dynamic viscosities. And now if you have to calculate some shear stresses dependent on velocity gradients, you need these different viscosity values. Here's an example, and that's some kind of student work. and it's a student work you should also do in your exercise. I will show it to you, I will explain it a bit to you, how to do it. And what you see in this exercise, we made a computational fluid dynamics with under CFX simulation, and we get a rotation of the swirl. And if you look here, it's water with 25 degrees. We get different swirls and different behaviors inside this tank than if you compare it with hotter water with 100 degrees. And this is because viscosity changes depending on the temperature, and then we get different results of our swirls inside the water. And that's something we want to do as exercise. Okay, let's have a short look at viscosity values for non-Newton fluids.